Okay, hello students, welcome to the next online course. Let me share my screen. Okay, you should now see the first page, photovoltaics, thin film solar cells.
Yes, we can see that.
Okay, this picture you have seen already. It just shall remind you of the main difference. Last week we talked about crystalline silicon technology, basically this green dashed framed part here. And now we talk about thin film technology, and the major difference is that we usually start with a glass or another substrate, but usually it's glass, and make then on the whole glass area the solar cells, and every of these stripes is a solar cell. As we will see later, they are inherently series connected with each other, and at the same time we make the module. That means the main difference between thin film technology and crystalline technology is that here in thin film technology, basically we make integrated the cell and the module together. Okay, let me first give you a definition what a thin film solar cell actually is. It's a solar cell of a thickness in the range of less than 1 micrometer or some few micrometers. And since they are so thin, they have to be made of a strongly absorbing semiconductor material. That means it must be a direct or quasi-direct. Okay, quasi-direct would be a more silicon semiconductor, else it would not work, because else one couldn't absorb sufficient light which is needed to get a reasonable conversion efficiency. That means, for example, silicon, crystalline silicon, since it's an indirect semiconductor, cannot be used as thin film solar cells. We need, for an indirect semiconductor, we need much bigger thicknesses. But this we treated last week. Okay, many of the thin film processes or deposition processes are vacuum processes. Example, for example, physical vapor deposition, which is either evaporation or sputtering, or chemical vapor deposition, which could be low pressure chemical vapor deposition or plasma enhanced chemical vapor deposition. Also atmospheric chemical vapor deposition is possible, which of course is no vacuum process, as the name says. And other non-vacuum processes which are used in thin film technology are just chemical bath deposition, screen printing, spin coating, or doctor plating. But in comparison to the real thin film technologies, these are rather thick film. I mean, I put it in quotation marks because this terminus technicus does not really exist, but these films are typical several 5 to 10 micrometers, and but usually cells made by these techniques are all the same still considered to be thin film solar cells. Okay, this picture gives you an overview of the 3 most important thin film technologies. And it's a typical layer sequence. That means we will certainly find deviations, but the majority of all the cells of this type will follow this layer sequence. And first, what we see, we always have a semiconductor here in light yellow, sorry, a metal gray And the TCO stands for transparent conducting oxide. That means TCOs are materials which are transparent as glass, but which are conductive with a higher conductivity as a semiconductor usually, but less than a metal. That means basically these are high band gap materials, usually insulators, but by a very high doping, these insulators become conductive. And these materials are very important, not only in thin film photovoltaics, but also, for example, for manufacturing thin film displays, for example. Because, I mean, it's clear if I can make an electrode which is transparent by itself, this is a really big advantage. Okay, let's start with the oldest of these materials and the oldest cell type in the market, which is amorphous silicon. And the A, of course, stands for amorphous, and the H stands for hydrogen, because this material is always hydrogenated. And if you start from the glass side, we first have the glass, then we have the TCO, which could be tin oxide or indium tin oxide. Then we have the p-doped layer, very thin. Then we have an undoped, also called intrinsic layer. And then we have the n-doped layer. And then we have a metal back contact, which also can be different metals. The cadmium telluride cell, you see it resembles this structure very much, because from the glass side, which is then of course the light incident side, we have again a TCO, which here is either tin oxide or cadmium tin oxide. Then the difference with respect to amorphous silicon is, you see in amorphous silicon we have a PIN structure. Here we have just an NP structure. That means we have an N-doped cadmium sulfide layer, and we have a P-doped cadmium telluride layer. And I should also notice these layers are not extrinsically doped. They are what is called intrinsic doping. That means the N-type or P-type character is created by some defects in this material. That means we don't have to add extrinsic elements to create this doping. The same is also the case for copper indium diselenide. This is also so-called intrinsic doping. Okay, and then we have the metal back contact. For the copper indium diselenide, also abbreviated CIS, we see the sequence is usually reversed. We start with the molybdenum, it's the metal back contact. In this material, only molybdenum works for some reasons. And then we have the PN sequence, where the copper indium and usually a part of the indium is replaced by gallium diselenide, which is the p-doped material, and again the n-doped cadmium sulfide. And in this type material, the only TCO which is usually used is zinc oxide. And I should add, all these TCOs are extrinsically doped, because else the conductivity would not be sufficient. But this is omitted here. This is usually implied if one talks about TCOs, that one needs an extrinsic doping for these materials. The amorphous silicon is the oldest cell in market, and you find it in many places. You also find it a lot of consumer electronics, which is widely used. And but for the power generation, basically it's no longer really competitive. And there are only a few manufacturers left in the moment. I will comment on this or explain why this is the case later. The cadmium telluride, it's the biggest thin film market share. That means almost 100% of the market share is this material, cadmium telluride, and mainly it comes from one company, the American company First Solar. And the third one, this copper indium gallium diselenide, this achieves the best lab efficiencies, lab efficiency is clearly above 20%, but it looks like that it's difficult to transfer this high efficiency to volume production. This is a challenge here, and this is also the reason why this has not become the dominating production technology yet. And one should also say in production, cadmium telluride and copper indium diselenide are roughly the same. Although the copper indium diselenide, if one looks at laboratory efficiency, obviously has a better potential, but this potential cannot be brought, at least until now, really to volume production. Okay, this picture you also have seen already. This time I will only focus on the green colors, which are the thin film technologies. And here you see the open circuit circles, which is amorphous silicon, and you see the amorphous silicon, and these are research efficiencies, you see, and the best amorphous silicon research efficiencies are roughly around 12%. 12% cell efficiency. And this is the reason why this material is no longer really competitive, because the efficiency is too poor and there was not really a progress in this material in the last, how to say, 2 decades or something like this. It looks better for the copper indium gallium diselenide, which are the full circles, you see, and the full circles really, we reach efficiencies above 20%. And the yellow filled circles, these are the cadmium telluride. You see, they are not so much worse than the 6. And therefore, of course, this is a material which still is very promising. And as said, I mean, it's a main thin film material which we see in volume production and, of course, also in the field. It's if you have usually, if you have a big PV power plant of thin film material, it's usually cadmium telluride, and usually from First Solar. This is just pictures of such thin film modules, how they look like. You see they look different. We don't see this single cell structure because the whole area is made in one production process. And in the middle, you see an older First Solar module. That means all these have typically, how to say, a dark color. And one should also emphasize, which unfortunately is not resolved here, but if you look at such a module, say at a distance of 2 meters or something like this, you see this already mentioned stripes. That means this stripe structure usually can be identified, and this is a clear sign that these are thin film modules. Okay, here I will show you the typical process sequence for manufacturing of a thin film solar cell. In this case, amorphous silicon, but the other technologies are analogous. The only thing, of course, which is exchanged is the deposition of the semiconductor material itself. But the TCO deposition, of course, is the same, and usually, I mean, it's either a sputtering process or a chemical vapor deposition process by which the TCOs are made. Then there follows a laser structuring. That means you see in certain intervals, and the width here is typically 1 centimeter, these whole area is separated into single stripes. This is just done by an ablative laser cut. Then we have the deposition of the semiconductor material. In case of amorphous silicon, it's just first dope material, either usually first boron dope, that means p-doped, from diborane, silane and diborane. Then you have the intrinsic layer only from a silane plasma, and then the phosphorus doped or n-doped from a silane phosphine plasma. It means here the deposition process is plasma enhanced chemical vapor deposition. And then we see we have again a laser structuring laser patterning. And this again is done with a small offset. We will see later why this is done in this way. That means especially these 3 deposition steps and the 3 patterning steps, I mean, they are the same for all the thin film technologies which I presented until now. Okay, this foil you saw already last week, and therefore I will only explain what is different in comparison to last week. Last week we focused on the anti-reflection coating. Now we will focus on this equation where the amorphous silicon is made from the silane and possibly hydrogen, because the material always contains some hydrogen. I will say later a little bit why this is the case. For doping, as already said, we just add phosphine or diborane, and we could also alloy it either with germanium or with carbon. This would adjust the band gaps. Alloying with germanium would make the band gap smaller, and alloying with carbon would make the band gap wider. And although in this way we can not only deposit amorphous hydrogenated silicon, we could also deposit microcrystalline silicon. I will explain later what it is, just by varying the hydrogen content in this first chemical reaction. And as I also mentioned already last week, this material is also important for the so-called HIT or heterojunction cell. This was a topic of last week. Okay, let me first show the band diagram of the amorphous silicon, and actually you saw it already in the second lesson as an example for a drift-determined cell, and it's actually the only purely drift-determined solar cell. That means, you see, this is the purpose of the intrinsic or undoped layer. The purpose of the intrinsic or undoped layer is just to extend the electric field, which is usually limited to the space charge region of the junction, across the whole cell. Because the electric field is always further extending the lower the doping of a layer is. And therefore, intrinsic means it's undoped, and therefore the electric field extends throughout the whole undoped layer. And it's needed, as already explained in the second tuition unit, because the diffusion lengths are so small in that material. Without the electric field as a charge carrier collection support, this type of solar cell would not work. Okay, this is the drift-determined cell in photovoltaics. All the other cell types are mainly diffusion-determined. And since the performance of a single, okay, here again the same is valid, just ignore the German text, read the English translation. Everywhere English translation is added. And since the performance of a single amorphous cell, it would be here the yellow one, is so poor, usually in commercial modules it's combined with a thin microcrystalline silicon layer. The light incidence would be from the top. That means the amorphous silicon would be the top cell, and the microcrystalline cell would be the bottom cell. Here, I mean just the spectral response of the two solar cells. The amorphous cell and the microcrystalline cell are compared to the sun spectrum as it's offered. And you can see the amorphous silicon cell uses this blue part of the spectrum, whereas the microcrystalline silicon cell uses this pink colored part. And in total, this so-called tandem device can use a bigger part of the spectrum than just a single cell can use. So that is in principle, this was the first tandem device, or one of the first tandem devices on the market. And it's a nice example how such a tandem cell concept can improve the efficiency. Okay, here we actually see what amorphous and also microcrystalline means. Amorphous means, of course, without a crystalline structure. You see what the cursor is now surrounding, that would be a amorphous part. We see in principle random distribution of the atoms. The only thing which is preserved is the next neighbors, or is almost preserved, is the next neighbors of a simple atom, but there is no long-range order. But on the other side, you see there are small crystallites, really microcrystallites. That means there are small regions where it's arranged, and therefore this is called microcrystalline material. If it would be completely random, then it would be amorphous material. And in the lower picture, in principle, we see the transition from a multicrystalline material or polycrystalline material to a purely amorphous material. And what is used in these tandem cells would be in the first cell, of course, with this to the very right, which is amorphous material, and for the second cell, something here in the middle, which is called microcrystalline, is used. And here you also see a TM picture, transmission electron microscopy picture, where we see here, for example, a microcrystal. And here, for example, we see an amorphous region. And the reason why this is done are the different absorption coefficients and also the different band gap of the material. You see the dotted line, that is a crystalline material. And we see the typical shape of an indirect semiconductor. Here the dashed line is amorphous silicon, and at least this steeper increase already resembles a little bit a direct semiconductor, and that is why this material is called a quasi-direct semiconductor. And the microcrystalline material, it's still similar to the crystalline material. That means it's really a crystalline material, and as we can see here also, it has a lower band gap. It has roughly the band gap of crystalline silicon, whereas the band gap, as we can see here, where we have this decay, because here we have a logarithmic scale on the ordinate, that means it's a really big change of the absorption coefficient. That is typical for, or this is firstly typical, of course, for a direct semiconductor, and secondly, it shows us that the band gap, of course, here is much bigger than the band gap of crystalline silicon. And therefore, of course, these two materials can use a different part of the spectrum or the electromagnetic spectrum. That means this is a principal concept of tandem or multi-junction cells, that we start with the highest band gap for the top cell and then stepwise decrease the band gaps. Okay, this is just a picture of such a PECVD deposition system, such an industrial systems. You see these are quite big substrates. It looks like a mirror here, and probably because it is obviously after the metal deposition. And this would be the counter electrode here on the right hand side, and you see also this shower head. I mean, this through these small nozzles, the reaction gases are let in. Okay, and this would be a picture of such a system. In this case, you see it's quite huge systems here. In this case, it would be by Applied Materials. Applied Materials is the biggest semiconductor equipment manufacturer in the world. It's an American company. And you see, but one should also say, since amorphous silicon is no longer competitive, Applied Material withdrew from this business. But for example, machines which are used for making flat panel displays look quite similar. And in basically, Applied Materials used its know-how from flat panel display manufacturing and transferred it to thin film photovoltaics. That means the technological concepts in thin film photovoltaics and flat panel display making are quite similar. Okay, let's come to the 6 and cadmium telluride cells, which are at the moment the most important. As I said already, the cadmium telluride, with respect to the production volume, as a copper indium gallium diselenide, you can also consider as a 2,6 semiconductor. That means the Roman numbers, they always refer to the group in the periodic table of elements, because you see the tellurium and the selenium are from group 6, of course. Cadmium is group 2, and copper would have valency 1, it's from group 1, and indium and gallium are from group 3. And that means copper and indium and gallium in average is group 2. That means we always have, in principle, at least if we take the average of these two metals, we always have a group 2 metal and a group 6 non-metal, which make up this semiconductor. Just opposite. You see, in the 6, we start with the metal back contact, then we have the semiconductor, and then we have the TCO. And this, the top side is the light incident side, and here it's opposite. That means here we first deposit the TCO, then the semiconductors, and then the contact. And you see, in this case, in principle, the substrate is, if we take the top as a reference for the light incident side, here the substrate is above the cell. And therefore, this concept is also called superstrate. The superstrate is nothing else than a substrate which is above. And the substrate, of course, a real substrate is below. Sub is Latin, means below, and super is Latin, which means it's above. Both these cells, you see, have one unfortunate fact. They contain the poisonous cadmium. I mean, here only as a thin buffer layer. In the cadmium telluride cell, of course, I mean, cadmium is the main constituent. And there's a lot of debate in the PV community whether it makes sense to use in a green technology such a poisonous element as cadmium. I mean, first, solar, of course, they say it's not a problem at all. But of course, you must get all these modules back for recycling. You cannot just deposit them on a normal waste deposit. That means you have to lead them into the recycling process, and in all steps of the manufacturing chain, of course, you always must be careful just to avoid that something happens with this cadmium. And on the other hand side, for the 6 cell, therefore, there's one attempt, and meanwhile, these cells are also on the market. You get these cells also with another layer than the cadmium sulfide layer here, but usually you lose a little bit conversion efficiency if you replace the cadmium sulfide by something different. Okay, let's have a look at the band diagram of the cadmium telluride cell, and those who don't tell this anything, you just forget it then again. But for the others, what we see here we see the white band gap material of the TCO. In this case, it's tin oxide, and here I also added the extrinsic dopant. It's usually doped by fluorine, and you see fluorine is group 7 in the periodic table, oxygen is group 6, and therefore if we replace an oxygen atom by a fluorine atom, we have one surplus electron, and this makes, of course, a p-type character of this material. Then here we have the p-doped cadmium telluride. I said already, no extrinsic doping is necessary. This is an intrinsic doping, which is just created by a certain non-stoichiometry of this material. And here we have the cadmium sulfide. And what we see is the cadmium sulfide has a bigger band gap than the cadmium telluride. Cadmium telluride has 1.5 4, which is near to the ideal band gap of a semiconductor material, of a photovoltaic material. If you remember the second lesson, when we considered the Shockley-Queisser efficiency calculations, and the cadmium sulfide already has a much bigger band gap, almost 1 electron volt more. Most of this difference we see at the valence band edge. At the conduction band edge is not quite clear. I mean, the probability is low that it's precisely the same, but it's not really clear whether the electron affinity, because I mean this difference here is basically determined by a physical quantity which is called the electron affinity, and basically it means the same as the affinities you know from chemistry. And you see both electron affinities are roughly the same. That means it's roughly, the band edge is roughly without any step. But in reality, of course, the probability that they are 100% the same is very low. That means in reality, we will have either a step here upwards or a very slight step downwards. But in first approximation, of course, it's 0. The difference is certainly less than 100 milli-electron volts. Okay, here's a band diagram of the 6th solar cell. It's quite similar. The only difference is you see here the copper indium gallium diselenide has a lower band gap. Here again we have the cadmium sulfide, and therefore in this material by sure we have here a step. But this step is also less than 0.1 electron volt, and of course there's also a certain uncertainty because it's not so easy to measure this step. And of course, one could now think that this step is an obstacle for the electrons going to the right contact, because the electrons, of course, have to go to the left and the holes have to go to the right. But you see, this is 100 at most 100 milli-electron volts. The average thermal energy, which is K roughly in the range of kT, at room temperature is 25 milli-electron volts. That means in principle there's sufficient energy here that the electrons are thermally activated above this barrier, and although this barrier is here, they can reach their contact. And I should also say, you see the cadmium sulfide layer here is very thin. It's less than 50 nanometers. So that's a thousandth, less than a thousandth of the thickness or diameter of a human hair. Okay, and you see this is another difference. You see here we have, in addition to the extrinsically doped zinc oxide, in this case the doping is aluminium. Zinc has valency 2, aluminium has valency 3. If we replace a zinc atom by an aluminium atom, again we have a surplus electron which makes a end doping of this layer. But here you see between the extrinsically doped zinc oxide and the cadmium sulfide, we have an intrinsic zinc oxide layer, which is also just a few nanometers, but it has been shown that this additional layer can really improve the performance of the cell. Okay, I promised already that I will explain in more detail how this inherent series connection of the cell works. And let me remind you, see, these are the 3 patterning steps. First one, the back contact is patterned. Then the second one, with a certain offset here, the semiconductor layer is patterned. Okay, in this case, the example cadmium telluride, cadmium sulfide, but it would be precisely the same for amorphous silicon or for copper indium gallium diselenide. And the last one, you see the TCO is patterned again together with the semiconductor layer. And finally, we get this structure. And if you look at the dashed line, we see that we have created here an inherent series connection, because you see the front contact here, it's directly connected to the back contact here, and then the current path, of course, is through of the stripe connected electrically to the back contact of the neighboring stripe. And this is easily reached by these three patterning steps. And I said already in the first picture that usually it's an ablative laser scribe. This is true at least for cadmium telluride and for amorphous silicon, but partially it's also mechanical scribing. I mean, this is in case of step 2 and 3 in the copper indium gallium diselenide technology. The reason is just that in this technology, the laser, which of course in general is the preferred tool, does not work so well, and therefore usually one still uses mechanical scribes there. Okay, this is about the deposition technology of copper indium gallium diselenide. And in this example, as it's shown here, I've chosen the co-evaporation process because this gives the best laboratory efficiencies. And what we see here, in principle, we have 4 evaporation sources, one for copper, one for gallium, one for indium, and one for selenium. And we see in a sort of conveyor, the substrates come here, they are heated. These are here ohmic substrate, or it could be either ohmic heaters or infrared heaters. But this by these wires is probably ohmic heaters here. And then just by controlling the temperature of these evaporation sources, the molecular beams coming out of the elements here and going towards the surfaces of these elements are controlled. And therefore, the composition of the film by these 4 elements, or the relative composition of the films by these 4 elements, is controlled. And of course, which is not really shown here, but of course it's a vacuum technology. We need a load lock. Then we have here, in principle, the evaporation chamber, and we have again a load lock, which makes the transition from the high vacuum back to the atmosphere. There's a second process, which is just sequential sputtering. That means the metals, copper, indium, gallium, are sequentially sputtered, and afterwards we have an anneal in a selenium-containing atmosphere, and at least in volume production, it gives the same efficiencies, and the few pilot manufacturers which are in the market use either of the 2 technologies. But this one, as I said, gives the best laboratory efficiencies. Okay, let's have a look at the cadmium telluride deposition technology, there's used a technology which is called vapor transport deposition. And in this vapor transport deposition... Oh, yeah. Sorry? Okay, there seem to be some disturbances. Okay, now it's gone again. Okay. Here we have a deposition vessel which is run at a pressure between 10 and 100 torr at a temperature of roughly 800 degrees centigrade. And you see here we have the cadmium telluride crystals. And then we have here the substrates coming, heating to roughly 600 degrees centigrade. And then we have a carrier gas, which is shown in the other. Here you see we have a carrier gas which comes into this heated volume of cadmium telluride. The cadmium telluride makes a phase transition from the solid to the gaseous state. That means a sublimation. And the carrier gas takes it with it and brings it here to the surface of the heated material, and here's a cadmium telluride layer is deposited. And you see you have a continuous feed actuator such that you have a continuous supply of this cadmium telluride which is sublimated. And since in principle carrier gas is bringing the evaporated or is a sublimated cadmium telluride to its substrate where it's deposited, and since by this carrier gas this vapor is transported, this is called vapor transport deposition. In principle, it's a form of evaporation technology, a special form of evaporation technology. Okay, then let me come. I said these are the three concepts which are presented now of the three materials which are dominating in production, but amorphous silicon, as I said, it at least for photovoltaics, for power applications, it's beyond already. It's because if you look at the module efficiency of crystalline silicon is still higher. That means we have less supplementary costs. That means, for example, for mounting, cabling, and so on. These supplementary costs are also a balance of system costs. And therefore, of course, at the moment, economically, the crystalline silicon technology has an economic benefit. That means this is the reason why also the thin film percentage was decreasing in the last years. But let us have now a look at some additional thin film concepts which are either quite interesting as this one, the so-called dye-sensitized solar cell, also called Grätzel cell after the inventor Michael Grätzel from Lausanne University. Or other concepts as we still see. Okay, this one is already quite old. You see the first publication by Michael Grätzel was in 1991 in Nature. And there he published 7 to 8% of this cell. And what we see, we have a glass substrate, again a TCO, a very thin platinum electrode, and then we have an electrolyte. You see this in principle is a liquid solar cell. But in newer days, this liquid electrolyte is also substituted sometimes by solid-state electrolytes. But the first one was really a liquid electrolyte, and therefore you see this is one of these cells which are still considered a thin film technology, but it's really thicker than just a few micrometers. And then we have flakes and balls of titanium oxide, which is also a rather high bandgap material. On this titanium oxide spheres, there sits the dye molecules. That means the dye molecules, they are the trigger for the light to electricity conversion. And this is why this is called a dye-sensitized solar cell. Okay, then we have again a TCO and then another glass substrate. And of course, it must be tightly encapsulated just to avoid that the liquid electrolyte flows out. But for a solid electrolyte, of course, this problem is not so severe. The problem is, you see, when Grätzel invented this cell, people were very, positive-minded about the future of this cell. But since those days, and now it's 30 years ago, you see, I hardly have seen any progress. I saw Professor Grätzel already at many conferences, and at every conference he promised soon there will be the breakthrough of this cell, but still it's not the case. What is true that this cell is very easily made. Meanwhile, in many schools, you see there are equipments where the schoolboys and schoolgirls build this type of cell by their own. But the problem is, of course, the low efficiency. Okay, meanwhile, it might have reached roughly 10%, but 10% is still not really competitive to other technologies, even if it's very very cheap, and the reason is just the bill of system cost, as I just explained. Low technologies always have a high bill of system cost, and since in the last decades, and it will be the further development in the next decade, the percentage of the solar cells itself within the total system cost decreases all the time. Therefore, the cost of the solar cell becomes less and less important, and the bill of system and the balance of system costs becomes more and more important. Okay, this is a band diagram and working principle of the dye-sensitized cell. Okay, the left-hand side is similar to that what we know. We see here the TCO, and here we see the titanium oxide. But here, of course, this is new, and this would be the dye. And usually ruthenium is used. Ruthenium embedded in some organic molecule. This is a metal organic substance. But the essential what we need is the ruthenium, and what is shown here is the so-called HOMO and LUMO. HOMO is the highest occupied molecular orbital, and the LUMO is the lowest unoccupied molecular orbital. And you see what happens? I mean, the light excites an electron from the HOMO to the LUMO, and then it can fall down here into the to the conduction band edge of the titanium oxide and then go to the right contact. For the hole, it's a little bit more complicated. It must use the iodine or the iodine redox system here. That means, in principle, an electron comes from iodine ion, occupies here this orbital where it's missing. The iodide is converted to the iodine, and then it can diffuse to the counter electrode, and at the counter electrode again an electron can be used to fill the missing electron up. That means, you see, this is now the first example where we use here an electrolyte instead of a solid for this at least one of the two contacts. Okay. And the next step in the development from the dye-sensitized solar cell was then the organic solar cell. You see, in the organic solar cell now, we have two of these materials where we have to consider the HOMO and the LUMO. And the HOMO and the LUMO of these two materials are shifted relative to each other. And one acts as an electron donor and the other acts as an electron acceptor. And you see, in the electron donor, the light excites an electron from the HOMO to the LUMO. Then it can fall down here to the LUMO of the electron acceptor, and then it could be transferred to an electrode. Optionally, we could have here a layer which is called an electron transport layer, which at the same time is a hole blocking layer. And here we also could have an additional hole transport layer, which is an electron blocking layer. And this electron transport layer is an N-doped organic semiconductor, and the hole transport layer is a P-doped organic semiconductor. That means, you see, organic semiconductors in principle can dope similar as inorganic semiconductors. And in principle, you see this picture shows us a principal concept. One side usually with TCO, which is the light incidence side. Then we have usually a metal back contact. I said already the EBL and HBL are optional. And this is in principle this green and blue color. These are the two organic semiconductors, the electron acceptor and the electron donor. And what we see here we have here, similar as we had it with the titanium oxide spheres, we have a sort of blended concept. That means we don't have really layered structures, we have a blended structure. And the reason for this blended structure is to increase the interface here very much. Because in principle here, it's only the interface which acts as a photoactive layer. The reason is because the diffusion lengths of the charge carriers are so small here. And therefore, by this blended concept, I mean, this is also a difference to inorganic photovoltaics. Then the electron and hole are separated, and the electron goes, and the hole goes here to that contact, and the electron goes to the opposite contact. And these organic solar cells, they saw quite an interesting development in the last 2 decades. But one should say what was more successful than organic photovoltaics, it was either organic transistors or even more organic light emission diodes. Especially organic light emission diodes really is a very big business at the moment, for example, for mobile phones or other equipment which needs some displays. In PV, the most interesting development of the last decade was the perovskites. And there was a real hype about the perovskites. And therefore, I want to show you here what a perovskite is. First, a perovskite in a narrower sense is just calcium titanate. And this is really shown what is here. Red, we see the oxygen ions, blue, we see the calcium ions, and green-gray, we see the titanium ions. And it's a simple cubic structure. I mean, here one can still recognize it's really a cubic structure. And in the wider sense, this calcium titanate is used as a sort of paradigm substance for any other substance with this structure ABX3. And A can be either methyl ammonia or this analogous substance. The B can be, usually it's lead, but lead again has a problem that it's poisonous, and therefore people work also on replacement of lead by tin. And the X is a halogen, can be either iodine, bromine, chlorine. Okay, in the A, as I said, it can even be alternatively cesium. Okay, this is what a perovskite is. And of course, in photovoltaics, what is interesting here at the right bottom, this structure, methyl ammonia, lead, and then an halogen. And if we have a perovskite cell by its own, there are 2 concepts. I mean, you see the right-hand side, it's a normal concept, just the layers, as we know it from normal inorganic photovoltaics. The left one, again, it would be this blended concept. For example, one again could use here this titanium oxide, and then the perovskite is just covering the titanium oxide. Here we see a small part of it. Again, we just increase the active area where the photovoltaic energy conversion can take place very much. This is the concept of this. This is the idea of this blended concept. Okay, here is the Venn diagram of such a perovskite cell. In principle, just here, this would be the cell. Then we have an electron transport layer and a hole transport layer, and the titanium oxide, which is a part of the electron transport layer, is optional. What we always need is here the TCO, which in this case is fluorine doped tin oxide. And here in the middle, again with a very good band gap, you see 1.55. It's near to the optimum. In this case, if we have the methyl ammonia lead iodide. But the most interesting application for this type of solar cells is as a tandem cell with crystalline silicon. And here we see an example, which was a Nature publication in 2020, where the efficiency of this tandem device was 25%. Meanwhile, it's more than 29%. And what we see here we have a crystalline silicon cell, which here is this HIT cell concept, as I introduced it last week. And this HIT cell is combined here with a perovskite cell. And here you see also an SEM picture. Here you see there's a silicon. Here you see the perovskite layer, which precisely follows the texturing. Here, from last week, I introduced this pyramid-like texturing, which is created by an alkaline edge. And these two cells together give this very high, this very promising technology. And meanwhile, for example, we have also already a company started here in Brandenburg in Germany, which is trying to bring this concept to volume production. Okay, the last cell type I would like to mention is the gallium arsenide-based multi-junction cells. And this picture shows the basic concept. This is an example for a quadruple cell. You see the bottom cell is germanium. Then we have gallium, indium, arsenic nitride. Then we have gallium arsenide. Then we have gallium, indium phosphide. And from top to bottom, the band gap is decreasing, and every part of this quadruple cell is using a different part of the electromagnetic spectrum. And these cells can be very high efficient under concentration. We can have efficiencies more than 40% or almost 50%. And you also remember from the second unit that in principle, we can approach by these concepts even higher efficiencies. The germanium part, of course, is in principle a wafer-based technology, but the others are just deposited by a metal organic CVD process, and therefore the 3,5 semiconductors, the gallium arsenide-based semiconductors, they are thin film technologies. And gallium arsenide, of course, is also a direct semiconductor. Okay, and here we see a real structure. You see the real structure is even more complicated. In this case, it's a triple cell, and we see here's the main layers, here gallium, indium phosphide, here gallium, indium arsenide, and here germanium. And we see a lot of additional layers, which of course all have their function, but which would be beyond the scope of this lesson. And the only thing what I mention here, because here I have this TM picture, you see here this so-called step-graded buffer layer. The sense is just to adjust the lattice constant of the germanium basis to the lattice constant here of the gallium indium arsenide cell, because the cell works the better, the less strained in the different materials is. And the lattice constants of these different materials, of course, are not 100% the same. And therefore, of course, it helps to have such a lattice constant adjustment. Okay, this is my last foil. And again, I am open for 2 or 3 questions if there are some.
Professor Bernard.
So which one has the best efficiency?
This one, which I show here, gallium arsenide, I just said you have efficiencies more than 40%.
Professor, could you please go to the very first slide of today? May I ask?
So which slide?
The very first slide of today's lecture. May I ask you a question from there?
Sorry, can somebody translate it to Oxford English? I don't get what he wants.
Slide number 1 of today. Am I audible?
Number one. Number one. Okay. Okay, here.
Probably the next one.
Next one. Okay.
Where it has been said that this one that you have said that to make a solar cell we need to use direct or quasi-direct semiconductors, but not the indirect semiconductors. Could you please explain why?
Yes, because an indirect semiconductor is absorbing too weakly. I mean, just the material of a few micrometers would not be sufficient to absorb sufficient light.
Is it only for the absorber material, or can I use indirect semiconductors in the window as well as the back surface layers?
Okay, I mean, for non-absorbing materials, of course, you could also use indirect semiconductors. But this, of course, is possible. I mean, here I'm only talking about really the photoactive layer. I'm not talking about support layers. I just talk about the photoactive layer, which really makes the conversion of light to electricity.
Thank you, Professor.
Yes, you're welcome. Okay, let me have a look in the question is a chat. Can you please increase volume a little bit? Okay, now it's too late. I hope you heard it all the same. And also, in principle, I can't increase it. I mean, I could have talked louder. Okay, and the second one, how much percent of efficiency thin film solar cells have? I mean, as I showed in this diagram, it varies from 10% for amorphous silicon to 20% of cadmium telluride or copper indium gallium diselenide. I mean, this would be already volume production efficiencies to more than 40% under concentration for the gallium arsenide based semiconductors. Okay, a further question, a last question maybe.
Professor Bennett. Yeah, I have a question. Yeah, that's
yes, so please ask it.
So deposition by co-evaporation, yeah, this layer. I mean,
yes, co-evaporation. Yes, okay.
Yes, and in this case, it must be a vacuum, or if it is not vacuum, it's also possible. Or
yes, sorry, can you repeat your question, please?
so in this case, it should be a vacuum, or if it is not vacuum.
Yes, so of course, this one is a vacuum process, of course. I mean, this is a vacuum process, else it wouldn't work. Because in principle, of course, it forms these evaporation sources. I mean, to get a sufficiently high or fast film growth. I mean, you must have basically a molecular beam which is not scattered at some molecules, and therefore, of course, you really need a low pressure.
Okay.
That means, of course, during evaporation, the process, of course, the pressure is a little bit higher just due to the evaporation sources. But before you start the evaporation process, you need a high vacuum, say at least 10 to the -6 millibars.
Oh, I understand. Thanks a lot.
Yes, you're welcome. Okay, so then thank you very much for your time, and meet you again next week. Okay, bye-bye.
Have a nice day.
Yes, you're welcome. Bye-bye. Yes.
Bye-bye.